we derived Runge-Kutta method of order 2 for solving an initial value problem dy by dx is equal to f of x comma y of x naught equal to y naught. And the method is given by yn plus 1 is yn plus half of k1 plus k2, where k1 is h into f of xn yn and k2 is h into f of xn plus h yn plus h into f of xn yn. So, given the initial value problem, we are required to compute the solution say at xn. So, we divide the interval x naught to xn into n equal subintervals of width h by means of points x1, x2, x3, etc. xn minus 1. So, that h is xn minus x naught divided by n, and obtain the values at x1 which we call as y1, at x2 y2 and so on. At xn minus 1 it is yn minus 1 and at xn it is yn, and information is given at x naught as y naught. So, we use this method for values of n equal to 0, 1, 2, 3 etc. up to n minus 1, and start with the information given at x naught, namely y naught. Use this single step method, which is an explicit method, and compute what y1 is, namely it is y at x1. Once you know the solution at x1, namely y1, it is as though you are solving an initial value problem dy by dx is f of x comma y with y at x1 is equal to y1. So, you again use the single step method and compute y2 which is y at x2, and continue this till you reach this point xn, at which the solution is yn, and it can be obtained using the method that we have written down. This is what is Runge-Kutta method of order 2. This we had derived earlier, and we would now like to make use of this method and solve a simple problem. So, let us solve the following problem. Dy by dx is given to be say y plus x by y minus x. The initial condition is y of 0 equal to 1. Your problem is compute y at point 4 by taking step size h as 0.2. Sometimes this will be worded like solve this problem in 0 to 0.4 with step size as 0.2. So, this indicates the step size that you need to take for solving this problem. So, you are asked to start at 0 and go up to 0.4 in steps of 0.2. So, you observe that that's the midpoint of this interval. So, your x naught is 0, your x1 is 0.2 and your x2 is 0.4. You have the information here and you are asked to get the information at x1 and x2, namely y1 and y2. And you are asked to solve this problem by Runge-Kutta method of order 2. So, let us see how we can obtain the solution. We already have derived Runge-Kutta method of order 2, and we know that we have to use this to obtain the solution of that problem. So, what is y1? y1 will be from here y0 plus half of k1 plus k2. So, that will be 1 plus half of k1 plus k2. What is k1? k1 is h into f of x0 y0. So, 0.2 times f of x0 is 0, y0 is 1. That is 0.2 times what is f of x0 y0? Look at this, the problem is dy by dx is f of x comma y. So, your f of x comma y is y plus x by y minus x. So, you have f of 0 comma 1. So, it should be 1 plus 0 by 1 minus 0. So, the value is 0.2. So, we now compute what k2 is. k2 is from there h into f of x0 plus h comma y0 plus h into f of x0 y0. So, h is 0.2 into f of x0 is 0, h 0.2, y0 is 1, h is 0.2, f of x0 y0 is 0, 1. So, this will be 0.2 into f of 0.2 comma 1 plus 0.2 times what is f of 0, 1? We have just now seen it is 1 plus 0 by 1 minus 0, that is 1. This gives you 1.2. So, you need to now evaluate f of 0.2 1.2, which will be y plus x by y minus x. So, you have 0.2 into f of this will be 1.2 plus 0.2 divided by 1.2 minus 0.2. So, that will give you 0.2 into 1.4 divided by 1, and that is equal to 0.28. So, k2 is 0.28. So, having computed k1, k2, we now can use them to find what y1 is. So, y1 will be 1 plus half of k1 is 0.2, k2 is 0.28. So, that will give you 1 plus half of 0.48. So, it will be 1.24. So, it tells you that the value of y at x1 is approximated by this y1, and that is going to be value of y at 0.2, and it is given by 1.24. So, you have obtained the solution at this point x1, and the value here is 1.24. So, as I said earlier, now we have information at this point, and we have to solve the differential equation given that y at 0.2 is 1.24. So, we again have to use RK method of order 2 and move one step ahead to reach the point x2 at which the solution is y2, and it can be computed. So, we work out the details of computations of y2, so that you are sure of how the steps are going to be. What is y2? Again, from the method that we have written, it is y1 plus half of k1 plus k2. y1 is computed just now as 1.24 plus half of k1 plus k2. So, we compute k1. K1 will be h into f of x1 y1. So, 0.2 times f of x1 is 0.2, y1 is 1.24, and f of x comma y is y plus x divided by y minus x. So, we substitute for y and x appropriately and find out this result. So, this turns out to be 0.2 into 1.44 by 1.04, and that gives 0.288 divided by 1.04, and it is 0.27692308. So, K1 is computed. We now work out the details for computation of K2. K2 is computed as follows. K2 is h into f of x1 plus h comma y1 plus h into f of x1 y1. So, it is 0.2 into f of x1 is 0.2, h is 0.2, y1 is 1.24, h is 0.2 into f of 0.2 comma what is y1? 1.24. This gives f of 0.4 comma 1.24 plus 0.2 times 1.44 by 1.04. So, we have 0.2 times f of x comma y. That turns out to be 1.51692308. So, this function has to be now evaluated. What is f of x comma y? It is again y plus x by y minus x. If you simplify your computations, you finally get this to be 0.34325069, and that is K2. So, having computed K1 and K2, we substitute in this expression and obtain what y2 is. It is 1.24 into half of K1 is 0.27692308 and K2 is 0.34325069. And if you simplify, you end up with value of y2 as 1.55008688. So, this y2 approximates the value of y at x2, namely y at 0.4, and its value is 1.55008682. And you are asked to solve this initial value problem in this interval 0 to 0.4 with step size 0.2. So, you are required to get the solution at 0.2 and at 0.4, and you have computed them, and so the final solution is 1.24, which is the value of y at 0.2, and 1.55008688, which is the value of y at 0.4. So, you have to carefully work out the details by substituting the values of xi and yi and computing the function f of xi yi while evaluating k1 and k2. We now derive modified Euler's method. We recall first what Euler's method is. Modified Euler's method solves an initial value problem of the form dy by dx is equal to f of x comma y, and the initial condition is y of x naught is equal to y naught. So, we considered earlier Euler's method and geometrically said that in an interval say x naught to x1, given the information at x naught as y naught, when we want to find what is the value at x1, namely y1, if the solution curve in that interval x naught to say x1 is y is equal to y of x, then approximate this solution curve in this interval x naught to x1 by means of a straight line which is a tangent to the curve at the point x naught y naught, having slope f of x naught y naught. So, we wrote down the equation of the line, namely it passes through the point x naught y naught, it has its slope as f of x naught comma y naught, and so y will be y naught plus x minus x naught into f of x naught y naught. If I drop the ordinate at the point x1 and the curve actually meets the ordinate say at this point, but I do not know what the curve is, I would like to approximate this ordinate. So, I drop an ordinate at x1, and if it meets this tangent line at some point, I take that as the value of y1, namely the ordinate at x1. So, when y is y1, x is x1, and this gives me the value of y1, namely y naught. If I take this to be h into f of x naught y naught. So, I have an approximation of the value at x1 to be given by y1, which is y naught plus h into f of x naught y naught. Now that I have the information at x1 y1, I can move on to compute what is the solution at the next point x2, which is such that x2 is x naught plus 2h or x2 is x1 plus h. Then in that case, by the same argument, y2 will be y1 plus h into f of x1 y1, and I can go on and reach the point xn at which I would like to find the solution, namely it is yn, which is yn minus 1 plus h into f of xn minus 1 comma yn minus 1. So, if I require the solution of this problem in the interval x naught to xn, I divide the interval into a number of equally spaced points with step size h and determine the solution at these points using Euler's method, which is based on the assumption that the solution curve in any subinterval of the form x naught to x1 or any subinterval of the form xi to xi plus 1 is approximated by a straight line passing through the point xi comma yi and having slope f of xi yi. That is what is Euler's method. It is a single step method, it is an explicit method, and we already have discussed the error that is involved at each step of the computation of the solution by Euler's method, and we said that the step size h must be very, very small, and it is a very, very slow process. And so, is there any possibility of modifying this method? Yes, one can obtain the method which is known as modified Euler's method by making use of the following assumption. So, what is the assumption in modified Euler's method? Let us see. In modified Euler's method, the solution curve in an interval of the form say x0 to x1 is approximated by a straight line segment say L, whose slope is the average of the slopes of the lines L1 and L2, where L1 is the line through x0 y0 and having slope f of x0 comma y0, and L2 is the line through the same point x0 y0 and having slope given by f of x1 y1. So, you may ask me, you do not know y1, you are trying to find out what y1 is at x1 when you are given the information at x0. So, what is the modification in Euler's method? Take this y1 as the value that is predicted by Euler's method. You know how to get y1 using Euler's method. So, given an initial value problem, first predict the value of y1 at x1 by Euler's method. Whatever you get as y1, denote it by y1 predicted value and evaluate f of x1 comma y1 p. That gives you the slope of the straight line L2 passing through the point say x0 y0. Now, take the line L to have its slope to be the average of the slopes of the lines L1 and L2. So, let us now write down the equation of the line L. What is equation of line L? This line passes through x0 y0 and has its slope to be the average of the slopes of these two lines. So, the equation is y minus y0 is equal to slope, namely half of slope of L1 is f of x0 y0 plus slope of L2 is what? F of x1 comma y1 predicted multiplied by x minus x0. What is this y1 predicted? Do you know that? Y1 predicted is nothing but, you go back to Euler's method. You predicted that y1 using Euler's method. What is that? It is y0 plus h into f of x0 y0. So, this is the equation of the line. Then how do you determine now a new value of y1 at x1 because of this modification? So, the new value is nothing but the ordinate at the point x is equal to x1. So, in this we substitute x as x1 and y as y1. So, we get y1 minus y naught will be equal to half of f of x naught y naught plus f of x1 y1 predicted multiplied by x1 minus x naught. But I know x1 minus x naught is the step size h. So, it is h by 2 into f of x naught y naught plus f of x1 y1 predicted, and therefore, this gives you a new y1, and that is equal to y naught plus h by 2 into f of x naught y naught plus f of x1 y1 predicted. This is the y1 which is obtained because of the modification that you incorporated in Euler's method. Namely, you modified the straight line approximating the solution curve in an interval x naught to x1 by taking that line to be one whose slope is the average of the slopes of the lines L1, L2. So, you obtain a new value, a modified value at x1 for y1. So, you say that you have corrected the earlier predicted value by Euler's method. So, you end up with a corrected value of y1, and here as we have already seen, the predicted value is given by Euler's method. So, this is the step that you should use to find solution at x1, namely y1. So, you have a predicted value of y1 and a corrected value of y1, which give you values at the point x1. So, you would like to check whether your corrected value and predicted value are such that the absolute value of the difference between the two is going to be less than the prescribed accuracy. Say it is something like 10 to the minus 3. If this happens, if call this a star, if star is satisfied, then you can stop your computations, and you have the solution correct to the desired degree of accuracy, which is y1 is equal to y1 corrected. If suppose star is not satisfied, let us see what has to be done. In that case, we write down y1 second corrected value and compute this value. What is y1 second corrected value? It is again by making use of this method. Instead of substituting y1 p here for y1, we can substitute y1 corrected value that we have computed here to evaluate this function. So, that y1 second corrected value will be y naught plus h by 2 into f of x naught comma y naught plus f of x1 comma y1 first corrected value. Earlier I used the predicted value by Euler's method and I corrected it. Now, I am unable to satisfy my requirement of accuracy, and therefore, I want to recorrect it, and I compute the recorrected value and denote it by y1 cc, in which I make use of the first corrected value that I obtain from here. So, we substitute and compute what y1 second corrected value. Here y1 corrected value has already been obtained. At this stage, I check if y1 second corrected value minus y1 first corrected value is less than epsilon, say 10 to the minus 3. If this happens, call this as double star. If this happens, then I stop the computation and write down the solution y1 as y1 second corrected value. If not, continue the computations till the desired degree of accuracy is attained. Degree of accuracy is attained. At every step when you want to continue, you must make use of the currently available corrected value of y1, and whatever you get is the new corrected value, and then you compare, you find the difference between the new corrected value and the previous corrected value and check whether your requirement is satisfied. If so, you stop. If not, you continue your computations. This is what is modified Euler's method is, and we observe that we have a nice predictor corrector method. Namely, I am able to predict the value of y1, which is the ordinate at x1, and I have scope for correcting it. Not only correcting it once, but I can make successive recorrections till the desired degree of accuracy is obtained. So, I can treat modified Euler's method as a predictor corrector method. We can predict the solution at a particular point and correct it successively till the desired degree of accuracy is attained. We will develop some more predictor corrector methods later on, but we started with a modification in Euler's method, which is a single step method, which is an explicit method, by simply modifying the assumption that in an interval the solution curve can be approximated by a line having its slope to be the average of the slopes of two lines passing through x naught comma y naught. We obtain a method. This is again a single step method, but we are able to get a predictor corrector method which helps us to predict the solution and correct it and recorrect it successively till the desired degree of accuracy is obtained. So, let us take an example and illustrate this method so that you know how to compute the solution using modified Euler's method. So, let us take this initial value problem. dy by dx is x plus root y. Initial condition given is y of 0 equal to 1, and you are asked to solve this problem in this interval 0 to 0.2 by taking step size as 0.2 using modified Euler's method, and determine the solution correct to the desired degree of accuracy, say epsilon, which is 10 to the minus 2. One can ask for more accurate solutions. Since we are doing manually, I take epsilon to be 10 to the minus 2. So, let us work out the details. So, always start with what is given, write it out clearly so that we know what is it that we want to compute. x naught is given to be 0, at which y naught is 1. We are asked to get the solution at point 2 and the step size is 0.2. So, x1 is 0.2 and the solution at x1 is required, correct to desired degree of accuracy. And we are asked to use modified Euler's method. So, the method will be such that if I want y1 at x1, it is y naught plus h by 2 into f of x naught y naught plus f of x1 y1 predicted, where y1 predicted is going to be y naught plus h into f of x naught y naught. So, let us first predict it. What is y naught? It is 1, h is 0.2, f of x naught is 0, y naught is 1. So, this will give you 1 plus 0.2 into, what is f of x comma y? This is f of x comma y, which is x plus root y. So, it is 0 plus root 1. So, it is 1 plus 0.2. So, 1.2 is the predicted value, and that is what I have to use here in getting what y1 is. Let us compute y1 now. So, y1 will be y naught, which is 1, plus h by 2 into f of x naught y naught plus f of x1 is 0.2, y1 predicted is 1.2, which will be 1 plus 0.2 by 2 into f of xy is x plus root y, f of xy is x plus root y. So, if you compute this, you end up with 1.2295. That is the value of y at x1, namely y1, obtained through modified Euler's method. If nothing is specified about the accuracy of your computation, you can stop here and say that the solution y at point 2 is 1.2295 and stop your computations, because you have not been asked to use modified Euler's method as a predictor corrector method. On the other hand, when some accuracy is specified and you are asked to compute the solution correct to the desired degree of accuracy, and you are asked to use modified Euler's method as a predictor corrector method, you cannot stop your computations here. You will have to continue your computations and call the value of y1 that you have obtained as the first corrected value and denote it as y1 corrected, which is 1.2295. And now recorrect it by using modified Euler's method. What is the recorrected value? y1 recorrected is going to be y naught plus h by 2 into f of x naught y naught plus f of x1 y1 first corrected value. So, you need to use the first corrected value here, and you observe that these terms remain as they are, y naught plus h by 2, f of x naught y naught, they appear also in your earlier computation. They remain as they are. The only change that occurs is here, where instead of y1 predicted value, you should use y1 corrected value. So, this will be 1 plus h by 2 into f of 0 1 x naught y naught plus f of x1 is 0.2. What is y1 corrected value? That is 1.2295. So, it is going to be 1 plus 0.2 by 2 into x plus root y plus x plus root y. So, compute this and you obtain y1 recorrected value. Suppose say you obtain its value to be some capital A. You can use your calculator and work out the details and get what this value of A is. At this stage, the difference between the second corrected value and the first corrected value, and if it is less than epsilon, the prescribed accuracy, then you stop. If this happens, you can stop. If not, continue your computations as explained earlier and get the solution at x1 correct to the desired degree of accuracy. You may ask me why at all you computed the second corrected value, because we immediately observed that the first corrected value is 1.2295 and the predicted value is 1.2. So, the difference turned out to be 0.0295 and we wanted an accuracy of 10 to the minus 2. So, at this stage, namely the first stage, we were not able to get our desired accuracy, and that is why we went on to computation of y1 again, namely we recorrected this value and tried to obtain the value A, and then we again have to check whether this condition is satisfied. If so, we can stop, otherwise we will have to continue our computations till the desired degree of accuracy is attained. I am sure you have understood the way in which the modified Euler's method has to be applied to an initial value problem, and the solution can be obtained correct to the desired degree of accuracy. We will continue with the discussion of predictor corrector methods in the next class. One predictor corrector method has already been obtained, namely modified Euler's method. That was not our intention, but we observed that it could be very nicely used as a predictor corrector method. So, we shall develop other methods which are predictor corrector methods for solution of initial value problem in the next class.